We are going to start now lecture 5 of chapter 8 class 11th mathematics binomial theorem. So in this lecture we will study some properties of the binomial coefficients and some problem based upon those properties. Now the first result we have is the greatest coefficient. So we are saying that if we have the binomial expression given to us, then we are talking about the expression of the form a plus b raised to the power n. If n is even, this power we are saying if it is even, then the greatest coefficient we have it is ncn by 2. And if this n is odd, then the greatest coefficients, we have two greatest coefficients, one is ncn minus 1 by 2 and second coefficient will be ncn plus 1 by 2. So we look at this problem now. First is show that the greatest term in the expansion of 1 plus x raised to the power 2n has also the greatest coefficients. This thing is given to us. Then x lies between n over n plus 1 and n plus 1 over n. So if we look at this expansion, it is 1 plus x raised to the power 2n, and we are talking about the middle term. Its middle term is 2n by 2 plus 1th term. So it will be n plus 1th term. And we are saying that the middle coefficient will have, this middle term has the greatest coefficient in this case. So what we obtain is that Tn is less than Tn plus 1 is greater than Tn plus 2. So we have two kind of inequalities over here. One is Tn plus 1 over Tn. We have it is less than, this value is greater than 1. And second is Tn plus 2 over Tn plus 1. This is less than 1. Now if we write the value of both these terms, we will have 2ncn into x raised to the power n divided by 2ncn minus 1 into x raised to the power n minus 1, and this value is equal to 2n minus n plus 1 by n into x, and this value we are saying it is greater than 1. So this implies us that x is greater than n over n plus 1. From this second inequality, what we obtain is that 2ncn plus 1 into x raised to the power n plus 1 divided by 2ncn x raised to the power n. We are saying this is equal to n over n plus 1 into x. And if this value is less than 1, so this thing implies us that x is less than n plus 1 by n. We have these two results. Now combining both these results, we obtain that n over n plus 1 is less than x is less than n plus 1 over n, and this is what we have to prove. Now next we have is show that the integral part of this expansion is odd, where n is a natural number. So this expansion we are saying it is 5 plus 2 root 6. We can write this is equal to 5 plus square root of 24 raised to the power n. N is given to be a natural number, and we have to prove that the integral part of this will be an odd number. So suppose we write 5 plus root 24 raised to the power n, it is equal to integral part, some fractional part is there, where the value of this f it lies between 0 and 1. And suppose we are saying that we have another number f dash which is 5 minus root 24 raised to the power n. And as this root 5 minus root 24, if we look at this number, we are talking about 5 minus root 24, this is less than 1. So this implies us that the value of f dash we have, it lies between 0 and 1. Now if we add these two equations, we are talking about, we have two equations. One is 5 plus root 24 raised to the power n, that is equal to I plus f, and second is 5 minus root 24 raised to the power n, that is the fractional part we are saying. And if we subtract both, add both these equations, we will obtain that 5 plus root 24 raised to the power n plus 5 minus root 24 raised to the power n, that is equal to I plus f dash. Now look at these two expansions. If we expand these terms, we will have nc0 5 raised to the power n plus nc1 5 raised to the power n minus 1 root 24 raised to the power 1 plus nc2 5 raised to the power n minus 2 root 24 square. And likewise we will have the other terms. The last term we will have, it is plus ncn root 24 raised to the power n. If we expand this second term, we are talking about the expansion of this second term, so it will be nc0 5 raised to the power 0 minus nc1 5 raised to the power n minus 1 root 24, then it is plus, then it is minus. So if we add both these terms will be cancelled, and what we are left with is 2 times nc0 5 raised to the power 0 plus nc2 5 raised to the power n minus 2. Look at this term, it is root 24 square, so that will be 24. Similarly, the next term we will be left with is nc4 5 raised to the power n minus 4 and 24 raised to the power 2 and so on. Now look at these terms over here, it is 24 square and so on. So all these terms we are saying these are the integer terms. These are the integer terms, and this number, it is a multiple of 2. So what we obtain is that this whole term we are talking about, this whole term will be an even integer. If this term is an even integer, we are saying this is f plus f dash. So what we have obtained from combining all these results is that I plus this f plus f dash, we are saying these are the fractional parts, these are numbers less than 1, but these are not equal to 0. So clearly this number will become I plus 1, because f plus f dash will be equal to 1, and that is equal to even integer, means it is some 2p. So this implies us that I is equal to 2p minus 1. So final result, we are saying it is equal to an odd integer. We are saying it is I is equal to 2p minus 1, it is an odd integer. And this is what we have to show, that the integral part of this number is odd. So a more general result in this regard, if we are talking about this number, it is square root p plus q raised to the power n. We are writing it is I plus f. We are writing square root p plus q raised to the power n. We are writing this is some I plus f, where the value of f, it lies between 0 and 1. We have to show that I plus f into f is equal to k raised to the power n, where p minus q square is equal to k is greater than 0 and square root of p minus q is less than 1. Now as we have discussed in the previous case, we start with this thing. We are saying that square root of p minus q, we are saying square root of p minus q, it is less than 1. This implies us that square root of p minus q raised to the power n is less than 1. It means square root of p minus q raised to the power n, we can write this is equal to some f dash, where 0 is less than f dash is less than 1. It is being given that square root of p plus q raised to the power n, that is equal to I plus f, where the value of f, it lies between 0 and 1. If we add or we are, in this case we are subtracting these two equations, we will obtain square root of p plus q raised to the power n minus square root of p minus q raised to the power n, that is equal to 2 times some integer value, because in this case what we are left with is square root of p raised to the power n minus 1 square root of p raised to the power n minus 3. Why? Because it is being given that n is odd, that is why we are subtracting these terms. We are left with the powers over here, it is n minus 1, n minus 3, and these n minus 1, n minus 3, these are now the even powers. So this square root p raised to the power some even number, that will give us p raised to the power something, so it will be an integer value. So we are saying that this is equal to an even integer. So we are saying that the LHS is also an integer. So what we have obtained, that I plus f minus f dash is also an integer. The value that we have calculated over here, that is also an integer. So what we obtain from this is, we are saying I plus f minus f dash is an integer, and the values of f and f dash, they lie between 0 and 1. So this thing implies us that f minus f dash, it is an integer. Now we are having two conditions. One is that 0 is less than equal to f is less than 1, and second is 0 is less than f dash is less than 1. We are talking about f minus f dash, it is an integer. So what we obtain is that 0, we have the values over here, look at these values. On subtracting both these results, we are saying minus 1 is less than f minus f dash is less than 1. And second condition we are having is that f minus f dash is integer. So both these condition implies us that f minus f dash is 0. So this implies us f is equal to f dash. Now if we calculate the value of I plus f into f, we are saying that is equal to I plus f into f dash. I plus f, we have the value, it is square root of p minus q raised to the power n, and f dash is square root of p plus q raised to the power n. And this is the value of this term, and this is the value of this term. This sign we have, it is plus sign over here. So we are getting it is p minus q square raised to the power n, and we are writing this is equal to k raised to the power n. So this is the general result, general form of what we have studied or what we have seen in our previous problem. Now next we have is, show that the integral part of this is even. So if we write this number in the form square root of 125 plus 11 raised to the power 2n plus 1, and we are writing, suppose this is equal to I plus f, and we have to prove that the integral part we have over here, it is even. So if we write the value of f, it is 0 is less than equal to f is less than 1, and suppose we are saying that f dash is equal to square root of 125 minus 11, and clearly the value of this f dash we have, it is lying between 0 and 1. So this power n is also satisfying the same condition, we are writing f dash is equal to this. Now if we subtract both these equations, we will have square root of 125 plus 11 raised to the power 2n plus 1 minus square root of 125 minus 11 raised to the power 2n plus 1. We have this is equal to I plus f minus f dash. Again, if we expand these terms, we will get the final answer is even integer, and in this case the value of f minus f dash that we will have, it will be equal to 0. So what we obtain is that I is equal to even integer, and this is what we have to prove. Next is let r is equal to 6 root 6 plus 14 raised to the power 2n plus 1, and f is equal to r plus greatest integer of r. That is, we are saying f is the fractional part over here. Then we have to find the value of r into f. Now we are saying this number 6 root 6 plus 14 raised to the power 2n plus 1, this is equal to square root of 216 plus 14 raised to the power 2n plus 1, and it is being given that r is equal to root 216 plus 14 raised to the power 2n plus 1. Now if we are writing r plus f is equal to this, we are saying this is equal to this value, where the value of f, it lies between 0 and 1. We are writing f dash is equal to root 216 minus 14 raised to the power 2n plus 1, where the value of f dash, it lies between 0 and 1. On subtracting both these equations, we obtain that greatest integer of r plus f minus f dash, that is equal to square root of 216 plus 14 raised to the power 2n plus 1 minus square root of 216 minus 14 raised to the power 2n plus 1, and what we obtain is greatest integer of r, that will be equal to, on subtracting these two terms, we will obtain it is an even number. This is an even integer. This thing we have already seen that if we subtract these values, we will get it is an even integer. So what we obtain from this is the value of f minus f dash, we have it is 0. So this implies us f is equal to f dash. Now we have to find the value of r into f. So that is equal to r into f dash. So that is equal to the value of f dash, we have it is this. So it is root 216 plus 14 raised to the power 2n plus 1 into root 216 plus minus 14 raised to the power 2n plus 1. So that is equal to 216 minus 196 raised to the power 2n plus 1. So that is equal to 20 raised to the power 2n plus 1. So this is the value of rf. Next is, if this value is equal to, we are saying it is 7 plus root 48 raised to the power n, that is equal to s plus t. It is given n and s are positive integer and t is the proper fraction. We have to prove that 1 minus t into s plus t is equal to 1. So we are saying that first equation we have it is s plus t is equal to 7 plus root 48 raised to the power n, where the value of t, it lies between 0 and 1. The second equation we have in this case, it is, say t dash is equal to 7 minus root 48 raised to the power n. 0 is less than t dash is less than 1. If we add both these equations, we get it is s plus t plus t dash, that is equal to 7 plus root 48 raised to the power n plus 7 minus root 48 raised to the power n. On adding both these values, we are saying that s plus 1 that is equal to 2 times p, that is it is an even integer. So if it is an even integer, so we are saying that we have t plus t dash is equal to 1. So this implies us that 1 minus t is equal to t dash. Now if we want to calculate the value of 1 minus t into s plus t, so it is equal to t dash into s plus t. So it is equal to 7 minus root 48 raised to the power n into 7 plus root 48 raised to the power n. So this is equal to 49 minus 48 raised to the power n. So that is equal to 1, and this is what we have to prove. Next is, if x is equal to, it is being given that x is equal to 8 plus, it is 3 root 7, so we can write it as root 63 raised to the power n, where n is a natural number. We have to prove that the integral part of x is an odd integer, and we have to show that x minus x square plus x into greatest integer of x is equal to 1. So this first part, that it is an odd integer, we have already seen that how we prove this result. It is 8 plus root 63 raised to the power n. We write it is greatest integer of x plus f. We write 8 minus root 63 raised to the power n is equal to some f dash. Value of f, it lies between 0 and 1, and this f dash lies between 0 and 1. Now if we add both these equations, we will obtain greatest integer of x plus f dash, that is equal to an even value. So we get it is greatest integer of x plus 1 is equal to 2p, or what we get is that f plus f dash is equal to 1. So this implies us 1 minus f is equal to f dash. Now coming, this thing proves that first part is being proved that it is an odd integer. This thing is clear from this, that greatest integer of x, we are saying it is 2p minus 1, so it is an odd integer. Now coming to the second part, we have to prove that x minus x square plus x into greatest integer of x is equal to 1. So we are talking about the equation, it is x minus x square plus x into greatest integer of x. We can write this is x minus x into, if we take x common, it is x plus minus greatest integer of x. So this x minus greatest integer of x, this thing means we are talking about the fractional part, so it is x minus x into f, and we can write it is x into 1 minus f. The value of 1 minus f, we have it is f dash, so it is equal to x into f dash. So what we obtain from this is that the value of x minus x square minus x into greatest integer of x, that is equal to x into f dash. It is equal to 8 plus 3 root 7 raised to the power n into 8 minus 3 root 7 raised to the power n, that is equal to 64 minus 63, that is equal to 1, and this is what we have to prove, that this result is equal to, this value is equal to 1. Now next we have certain problems based upon the binomial coefficients. So the first is, when each term, first case we are having is when each term of summation contains the product of two binomial coefficients or square of binomial coefficients. So in these kind of problems, what we have to do is, we are saying if the difference of lower suffixes of binomial coefficients in each term is same, we are talking about c0 c2 plus c1 c3 plus c2 c4 and so on. So we are talking about the lower suffixes over here. The difference between these two is 2, the difference between these two is 2, the difference between these two is 2. Then in the first case we are saying if each term of the series is positive, then we are talking about 1 plus x raised to the power n, that is equal to c naught plus c1x plus c2x square plus so on up to plus cn x raised to the power n. Now if we interchange 1 and x, we will have x plus 1 raised to the power n, that is equal to c naught x raised to the power n, c1x raised to the power n minus 1, so on up to plus cn. Now to find this kind of answer, what we will have to do is we have to multiply both these equations and we have to equate the coefficients of suitable power of x on both sides. Or another way to solve these kind of problems, this is another way we are saying to solve these kind of problems, it is we have to replace x by 1 by x and we will obtain it is 1 plus 1 by x raised to the power n, that is equal to c naught plus c1 by x so on up to plus cn by x. In place of doing this, we are writing it is 1 plus 1 by x is equal to this. Then multiplying these two equations, we are saying we multiply the equation 1 and equation 3 and we equate the powers on both sides. So this process or this thing will be more clear to you with the next example. So first is if 1 plus x raised to the power n is equal to this, we have to prove that c naught cr, c1 cr plus 1 and this value is equal to this. So clearly what we have over here, it is c naught and cr. So difference between both these, it is r. For the next two the difference is r, for the next two the difference is r. So what we are going to do over here is we are writing the value of 1 plus x raised to the power n, that will be c naught plus c1x so on up to plus cn x raised to the power n. We are going to write the value of x plus 1 raised to the power n, so that will be c naught x raised to the power n, c1 x raised to the power n minus 1, so on up to cn. Now if we multiply both these equations, we are talking about 1 plus x raised to the power 2n. We are multiplying both these equations. So what we obtain is these two terms will be multiplied, it is c naught cn. Then we are talking about the terms with power x, we are saying it is plus x. So that will be c naught cn minus 1 plus c1 into cn. Next we are writing it is x square into, we are talking about the terms with power 2. So that will be this c naught will be multiplied with cn minus 2 plus c1 will be multiplied with cn minus 1 and c2 will be multiplied with cn. So what we obtain from this is, look at these two terms. The difference, this term is 0, this is n minus 2, this is 1, this is n minus 1, this is 2, this is n. So if we continue in this way and we write x raised to the power r, so we will have c naught, with this the value we will have it is c n minus r, then it is plus c1 cn minus r plus 1, so on up to the last term we will have, that it will be cr into cn. And if we write the term x raised to the power n minus r, that will be c naught c n minus n plus r, these two terms get cancelled, plus c1 cr plus 1, so on up to cn minus r cn. And this is the left hand side over here. So we are basically interested in the coefficient of x raised to the power n minus r in the expansion of 1 plus x raised to the power 2n, and the coefficient of this term will be 2n cn minus r. So we are saying the value of this term is 2n cn minus r, that is equal to 2n factorial over n minus r factorial into 2n minus n plus r factorial. This is n plus r factorial, and this is what we have to prove. So we have obtained this result. Now if we substitute r is equal to 0 in this, we obtain this first result, that is c naught square plus c1 square so on up to plus cn square, that is equal to 2n factorial divided by n factorial square. If we substitute r is equal to 1, we get c naught c1 plus c1 c2 so on up to cn minus 1 cn, that is equal to 2n factorial over n minus 1 factorial into n plus 1 factorial. If we substitute r is equal to 2, we obtain the result in this form. Now the second case we are saying is that if in the question it is being given that if the terms of the series they are alternatively positive and negative, then we are talking about two expansion. One is 1 minus x raised to the power n is equal to this. Second is x plus 1 raised to the power n is equal to this. Again we multiply both these expansions. We multiply both these and equate the suitable powers. Or what we are going to do, we are going to replace x by 1 by x, and we are going to find the expansion of 1 minus 1 by x raised to the power n. We obtain this expansion, and again by equating the suitable powers we will obtain the answer. So the question based upon this is, it is 2n c0 square 2n c1 square, it is minus sign over here then plus sign over here, so alternate signs are there and we have to prove that it is equal to this value. So to solve this kind of problem, we have written the expansion of 1 minus x raised to the power 2n. We have written the expansion of x plus 1 raised to the power 2n. We are saying if we multiply both these values, we will obtain x square minus 1 raised to the power 2n, and the coefficients we obtain it is in this form, and this is basically the left hand side of this equation. Now we are saying that this term when we multiply it can be written in the form 1 minus x square raised to the power 2n, and the general term for this tr plus 1, that is equal to 2n cr minus x square raised to the power r. Now if we substitute this r is equal to n, we will obtain tn plus 1 is equal to 2n cn minus x square raised to the power n. So this is equal to 2n cn minus 1 raised to the power n into x raised to the power 2n. So we are saying that the coefficient of x raised to the power 2n in this term, it is minus 1 raised to the power n 2n cn, and if we are writing the coefficient of x raised to the power 2n in the product of these two terms, it is this left hand side we have obtained, and from this calculation we have obtained this right hand side. So we have proved this result. Next is, if the sum of the lower suffixes of the binomial coefficients in each term they are same. In the previous case, in place of sum we were talking about the difference was same. Now we are saying the sum is same. We are talking about the conditions like this, that c naught cn plus c1 cn minus 1 so on up to cn c naught. We are having the terms in this way. So we are saying the sum of these is values, it is n. The previous case it was the difference. Now we are talking about the sum is constant. So again the first case we are saying, if each term of the series is positive, then we are going to write the expansion of 1 plus x raised to the power n is equal to this. We are going to write the same expansion over here, same expansion we have written again, and we are going to multiply these two equations and equate the suitable powers of x on the both sides to obtain the required answer. So the question we have over here, it is, we have to prove that m plus ncr is equal to this value. Now over here we have the term, it is nc0. So sum of both these it is r, sum of both these it is r, sum of both these values it is r, sum of both these values it is r. So what we are going to do is, we are going to write the expansion of 1 plus x raised to the power m. This expansion is being written over here, 1 plus x raised to the power m. We are going to write the expansion of 1 plus x raised to the power n. We are having two different coefficients over here, m and n. When we multiply these values, we obtain the answer in this form. We multiply these two equations. This is our first equation and this is our second equation. When we multiply both these, we are getting the answer in this form. And if we equate the coefficient of x raised to the power r on both sides of this equation, we are having 1 plus x raised to the power m plus n. We obtain the required result. If we equate these values, we obtain this required result. Next is, if the terms of the series, they are alternatively positive and negative, then we are going to write the term 1 minus x raised to the power n. We are going to write 1 plus x raised to the power n. We are going to multiply those terms and equate the suitable powers. So the problem is in this form. It is 1 plus x raised to the power n is equal to this, it is given. We have to prove that this value is equal to 0 or this value is equal to this, accordingly as n is even or odd. So again we have written the expansions over here. I am not writing the expansions again and again. This is the expansion for 1 plus x raised to the power n. Both the values, these are n. So we are writing 1 minus x raised to the power n. If we multiply both these equations, we are writing it is 1 minus x square raised to the power n is equal to product of these two expansions. Now equating the coefficients of x raised to the power r, we obtain this is equal to this value. If we write the coefficient of x raised to the power n and we write the general term, the nth term, to find the coefficient of x raised to the power n, and we put 2r is equal to n. Now if we try to find the coefficient of x raised to the power n in the LHS value, we obtain the answer, it is this, that is equal to this value, and it is equal to 0 if n is odd, and it is equal to this value if n is even. So on equating the both sides, both LHS and RHS, on equating both these values, we obtain that the value of this expression, it will be equal to 0 if n is odd, and it is minus 1 raised to the power this if n is even. Why? For odd we are saying, we have the value over here, it is ncn by 2, and if we consider the value of n to be odd, then clearly this value will be equal to 0. Now the next case we have is, if each term is the product of two binomial coefficients divided by or multiplied by an integer. We are saying the terms we have over here, it is c1 square, then it is product of two binomial coefficients and an integer is there, an integer is there, an integer is there. Then in this case what we have to do is, I am explaining over here with an example. We are writing the expansion 1 plus x raised to the power n is equal to this. Now what we have to do in this case is we have to differentiate this equation on both sides, and the answer we obtain on differentiating this is the expansion we obtain. It is n into this term. So we have transformed this given or this first equation in this form by differentiating it. We have obtained the coefficients over here. It is 2, 3, n, and these are the answers we require over here. And then we have written the expansion of x plus 1 raised to the power n in this form. When we multiply both these equations, we get it is n into this value, n into 1 plus x raised to the power 2n is equal to this. It is the product of these two terms. Now again, if we equate the coefficient of x raised to the power n minus 1 on both sides, we will obtain the required answer. We have equated the coefficients of x raised to the power n minus 1 on both sides to obtain the answer. Next is, if we have the question in this form, that we have to prove the result as c0 square plus c1 square by 2 plus c2 square by 3, so on up to this value. So it is clear from this result that we are having 2, 3, n plus 1 in the denominator. So we have written this expansion. This is being given to us. What we have done, we have integrated this value. We are going to integrate this value, and we obtain the expansion in this form. We are having, this is the new expansion we have obtained. Now the second, this is our equation number 1. The second equation we are writing corresponding to x plus 1 raised to the power n. When we multiply both these terms, and we equate the coefficients of x raised to the power n, we obtain the required answer. So you can try these calculations at your own. We are saying we have multiplied both these values, we obtain this result. Then we are talking about the value of the coefficient of x raised to the power n plus 1 in the expansion of the result we have obtained over there. It is 1 by n plus 1 cn plus 1 minus 0. On equating both these results, we obtain the required value. Next, we have some problems in the form that there is a binomial inside another binomial. So we are saying we have to evaluate the value of, first question we have, it is sigma r is equal to 0 to n plus r cn. So we are writing this is equal to, if we substitute the values of r, we have n cn plus n plus 1 cn plus n plus 2 cn, so on up to plus 2n cn. What is NCN? It is the coefficient of x raised to the power n in expansion of 1 plus x raised to the power n. Next term it is 1 plus x raised to the power n plus 1, so on up to 1 plus x raised to the power 2n. This is a finite GP. So we are talking about this is equal to coefficient of x raised to the power n in, now the terms we have, it is 1 plus x raised to the power n into 1 plus x raised to the power n minus 1 over 1 plus x minus 1. So we obtain this is equal to coefficient of x raised to the power n in expansion of 1 plus x raised to the power 2n plus 1 minus 1 plus x raised to the power n. So if we write the value of this term, coefficient of x raised to power n, it is 2n plus 1 cn plus 1, and the coefficient of x raised to the power n in this expansion, it is 0. So the answer we obtain, it is 2n plus 1 cn. This is the answer we obtain in this case. Next is if it is given that 1 plus x raised to the power n, this is the expansion given to us. We have to prove that C naught 2n Cn minus C1 2n minus 2 Cn. Now it is important to see over here that these values, we are saying it is n over here, it is 2n over here, it is n over here, it is 2n minus 2 over here. So these values are being changed. So it is not the question of the kind that we have already discussed. So what we are going to see over here, it is, we are saying we have nc0 into 2ncn minus nc1 2n minus 2cn plus nc2 into 2n minus 4cn, the terms in this way. So we can write this is basically C naught into 1 plus x raised to the power 2n. We are talking about coefficient of x raised to the power n in expansion of this, minus C1 into 1 plus x raised to the power 2n minus 2 plus C2 into 1 plus x raised to the power 2n minus 4 and so on. So this value we can write, it is C naught, we are talking about coefficient of x raised to the power n in expansion of 1 plus x square raised to the power n. This C naught is outside over here. Next we have is minus C1 1 plus x square whole raised to the power n minus 1 plus C2 into 1 plus x square whole raised to the power n minus 2 and so on. So we are saying this is coefficient of x raised to the power n in expansion of, we have the term, it is 1 plus x raised to the power 2 minus 1 raised to the power n. So if we solve this value, it is 1 plus x square plus 2x minus 1. So we are writing this is coefficient of the power x raised to power n in the expansion of x into x plus 2. So we are saying this power n, we are saying, so it is x raised to the power n into x plus 2 raised to the power n. It means we are interested in the constant term. We are talking about, look at this condition over here, we are saying coefficient of x raised to the power n in the expansion of this term. It means we are saying that the constant term in the expansion of x plus 2 raised to the power n, because when this constant term will be multiplied with x raised to the power n, we will get the coefficient of x raised to the power n, and the constant term over here, it is 2 raised to the power n. So this is what we have to prove, that this value is equal to 2 raised to the power n. Now next is, if 1 plus x raised to the power n is equal to this value, we have to find the values of these terms. So the first part we have, it is sigma I is equal to 0 to n, sigma j is equal to 0 to n, ci plus cj. Now this is equal to sigma I is equal to 0 to n, sigma j is equal to 0 to n. We are writing cj, second term will be same, so we are writing 2 times over here. Now what is sigma cj? J is equal to 1 to n. We are saying c1 plus c2 so on up to plus cn. We know that the value, it is 2 raised to the power n. So answer we get, it is 2 times sigma I is equal to 0 to n 2 raised to the power n. It is constant term over here. It is being added n times. So we are getting, it is 2 times 2 raised to the power n. How many terms are there? It is n plus 1 terms are there. So we are getting, it is n plus 1 over here. We are saying 2 raised to the power n plus 2 raised to the power n. This is added n plus 1 times. So answer we are getting, it is in this form. So the answer, final answer we obtain, that is equal to 2 raised to the power n plus 1 into n plus 1. Second part we have, it is sum of these values. So we can write it as sigma I is equal to 1 to n, sigma j is equal to 0 to, both these values, this is 0 to n, it is I ci cj plus sigma j ci cj. So if we look at this value over here, we can write this is equal to sigma I is equal to 0 to n ICI sigma Cj, and this total value we are writing, it is 2 times of this. Now what is the value of sigma Cj? It is 2 raised to the power n. So we get it is 2 times this value, it is 2 raised to the power n. Sigma I is equal to 1 to n I into Ci. This power n, this is not over there. Now to solve this value, we are writing this is 2 raised to the power n plus 1 sigma I is equal to 1 to n. Now this value we are saying this is nci, and we can write this is equal to n by I, n minus 1 ci minus 1. This is n by I over here, so this I gets cancelled. We get it is n into 2 raised to the power n plus 1 sigma I is equal to 0 to n ci minus 1 to n minus 1, and this sum will be equal to 2 raised to the power n minus 1. So we get it is n into 2 raised to the power n plus 1 into 2 raised to the power n minus 1. So this is equal to n into 2 raised to the power 2 n, and this is what we have to prove. It is n into 2 raised to the power 2n.